So like I said, the radial distribution function is the probability of finding the electron in a spherical is S of R, right? Which is R squared times the radial function squared. Okay. So if you want the probability of finding an electron in a spherical shell of radius R, so you have a shell that has a radius of R and a thickness of dr. So the thickness of your shell is dr. Is S of R dr. That's the probability of finding the electron. Okay. So what would be the probability of finding the electron within a sphere centered on the nucleus with a radius of A0? How would you set up that integral? All you have to do is integrate your S of R dr from 0 to A0. Okay? Or you can say integral of R squared, big R squared dr from 0 to A0. That's the answer to that question. Little r squared times big R squared dr. This is just the expression for your surface density or radial distribution function. What's the condition that's satisfied at the most probable distance? The most probable distance, your maximum S, right? At the most probable distance. So R most probable. At R most probable, what's the condition that's satisfied there? The derivative of S with respect to R must be equal to 0. Okay. So if you know the expression for S or for R, the radial function, take the derivative of that, set it equal to 0, you can find where the maxima is for that. Maximum values are for that function. What would be the integral that you need to calculate the average distance of the electron from the nucleus? The average distance would be that, right? And that's just going to be psi star times R times psi d tau. You integrate over all possible space. Now, since this does not depend on theta and phi, the quantity you're calculating doesn't depend on theta and phi, okay? You can just factor out all the thetas and phis from this integral right here, and you'll just end up with R times S of R dr from 0 to infinity. So, in fact, if you want to calculate of anything that depends only on R, the average value, okay, the average value of any function of R would just be the integral from 0 to infinity of f of R times S of R dr. And you just look up the actual expressions for S of R, or the radial function. Okay, so that's the average value of R. That will give you the average location, average distance. What would you need to calculate the average potential energy of the electron? What's the expression for potential energy? Potential energy depends on R, which is positive 1 over 4 pi epsilon naught times positive ZE. That's the charge of the nucleus. The charge of the electron is negative E over R, R being the distance of the electron from the nucleus, right? So that's your potential energy. So how do I get the average potential energy? Well, this whole thing is just a constant. I can just pull that out of my integral, right? So that's going to be 1 over 4 pi epsilon naught times negative ZE squared, okay, times the average value of 1 over R. What's the average value of 1 over r? This is just the integral of 1 over r times s of r dr. You can do this with psi, but then when you integrate over all the angles will just factor out, and you'll just end up with this expression like this. So this is from 0 to infinity. So that's your average potential energy. Okay. And that's how those are the kinds of information you can get from the radial distribution function.